First modification. Y equals a times the sine of x. Capital A is going to be a variable for us. It's not going to be a variable. That's the wrong word. Capital A is going to be a constant. So our curve now is a times the sine of x. So this is not a particularly large change, but we do need to talk about one aspect of the sine curve that we didn't talk about before, and that's what we call the amplitude. Amplitude is going to be sort of our like max, minimum distance from the middle of our curve. So it's essentially how tall are our sort of peaks and valleys, right? So for our standard sine function, y equals sine of x, our amplitude is just +1, which means our sort of maximums and minimums happen at positive and -1. That's what we saw in the table, right? When we did our table of values, we have a middle, and then a max, and then a middle, and then a minimum, and then a middle again. So the middles are at 0, and our maximum and minimum were at sort of +1 and -1 respectively. So what's going to happen here is if I throw some sort of constant in front of my sine curve, if I sort of multiply a function by some number out in front, it's going to be either sort of a vertical stretch or compress. And which is which really just depends on the size of the number. The bigger the number, then it will be a stretch. If you're larger than 1, it will sort of stretch and get taller. If you are less than 1, if you're multiplying by 1/2 or 1/3 or 2/7, the curve will actually compress down towards the center, and it will be less tall. It will be more condensed. So what's going to happen for us here is our amplitude is going to be equal to the absolute value of a. So whatever that value is, a in front of the sine curve, the absolute value of that's going to be our amplitude. This means, in theory, we need to sort of talk about a positive or a negative case. We'll get to that. So this means then our sort of maximums and minimums will happen at plus minus a. What else changes? Literally nothing. So the period, right, is our cycle length is exactly the same, is still 2 pi, and so then that kind of implies that our sort of 5 key points that we need to sort of make our table will just sort of be the usual suspects. So the first one is 0, right? The second one is pi/2. These are just like quadrant angles. The third one is pi. The fourth one is 3 pi/2. And our fifth one is 2 pi. So let's take an example and like graph it and make a table and sort of go all the way. This will sync up with, right, this will be our mid, this will be our max, this will be another middle, this will be our minimum, and this will be back to the middle. So middle, max, middle, minimum, middle again, back to the beginning. Let's take something fairly plain. How about y equals 3 times the sine of x? Okay. So what's going on here? A value is 3. So our amplitude is the absolute value of 3, which is of course positive 3. So we will have maximums and minimums at positive -3. So if I start to make my table, my 5 key points, so x's and y's, The x values, right, are just going to be our usual values: 0, pi over 2, pi, 3 pi over 2, 2 pi. So those aren't changing at all. Our middle values, so what's the correspondence, right? This is middle, this is max, this is middle, this is minimum, this is middle again. So all my middle values are still at 0. 0, 0, 0, no big deal. The only thing that's changing are my maximums and my minimums. So my max is at positive 3, my minimum is at negative 3. And then if I sort of continue the curve, right, I can make a sketch from there. And if I wanted to continue it and keep it going, you can imagine that it would still have those same maxes and mins, and it would sort of keep the cycle going at the same rate. One of the things that's going to happen when we do these sketches, no reason to try to save space, we'll just sort of do it down here. I'm going to kind of lean on, right, that first rotation at 0 to 2 pi. This is really going to be where our sort of main positioning is. In theory, right, there's other stuff going on to the left and other stuff going on to the right. But we're maybe going to not emphasize those values quite as much. So 2 pi, 1 pi, we'll do our sort of quarter values, right? 0 is here, so this is going to be pi over 2. This would be 3 pi over 2. And so what are we really changing from the last graph? Well, the only thing we're changing really is the height of our curve. How tall does it get? So instead of only going to 1, it's going to go up to positive and negative 3. This means, again, we're playing a little bit sort of fast and loose. With our scaling, we kind of just make the scale on each axis to be whatever we need it to be to make a nice curve. You could sort of make an argument, right, that in some sense when you do that, you're really just sort of drawing the same shape over and over again, and you're kind of just like drawing an axis to fit it. That would be true. I would agree with that. That is true. That's true and is totally fair. So we've got 0, 0 is our 0.1. So pi over 2 are 90 degrees. So that's up at our maximum. So that's all the way up to 3. You can kind of tell relative to the other graph that we did, our original sine graph, this one's going to look a little bit steeper. So that's good. It would maybe be a little bit psychologically strange if it didn't look different at all. Middle here, this is going to be down to our minimum, which is minus 3, and then back to the middle. So try to draw a curve, connect them up. Peak, down through, and up again. That's about as nice a curve as I'm ever going to draw, so glad we got it on video. We should always write, never just draw this. I mean, obviously this is sort of the main focus. I just, for the sake of argument, I kind of just like to draw the next one a little bit dotted just to kind of show, okay, so one cycle is here, and this is sort of just repeating to get to these other ones. There's no real reason to draw it dotted. I guess I'm only doing that to emphasize how long one cycle is. Is that helpful? Who's to say? Hopefully it's not helpful. So this is y equals 3 times the sine of x. So it's really just this one change, right? And so part of what's going to happen as you're doing this is you kind of get practice drawing the original curve when you draw these new ones. What I'd like to do next is, I said something about, you know, absolute values, right? So what would happen if we did a negative value, a negative a? I'll also throw 2 curveballs in. So let's graph y equals, let's do negative 1/4 times the sine of x. So this is 2 things going on. This is a negative a value, and it's also an a value that's smaller, right? This is an a value that's less than 1. Nevertheless, for the most part, we're still going to operate on the same things. So a is negative 1/4. My amplitude is just going to be the positive version as my absolute value. So my amplitude is 1/4. That means my kind of maximum and minimum are going to happen at positive negative 1/4. So right off the bat, right, one of the things that's happening for us here is this version of the curve is going to be much more condensed vertically. This is going to be sort of vertically compressed version of the curve. It just doesn't have the same amplitude as the other one. The negative sign, what does that do? So if I have an a value that's less than 0, right, a negative a value, what that does is it flips the sine curve over my x-axis, right? So if y equals sine of x behaves like this, a negative version so it still hits these sort of middle points at the same rate, but the whole curve gets flipped. So instead of going up here, you're actually going to start by dropping down, then you're going to come back up, cross over, and keep going. So it's the same kind of movements, the same heights, the same everything, but what happens now is we've sort of flipped over the x-axis, right? We've sort of flipped over this curve, and so instead what we're going to have now is a middle, a minimum, a middle, a maximum, and a middle. So we have the same 5 key points, but the pattern has changed a little bit. The points still happen at the same values, right? Those quadrant angles. Let's start filling in our table as we talk. So xy, so 0, pi over 2, pi, 3 pi over 2, 2 pi. So those angle values, the x input values, aren't changing. What is changing, right, is now I have a midpoint, and then I drop to the minimum, then I have a middle, then I rise to the max, then I'm back to the middle, right? So it's sort of a drop, an up, and then a drop again. I flipped the curve upside down. That last line was sort of unnecessary. What are my actual maximum and minimum values? So the middle points still happen at 0. This, right, maximums, minimums are now happening at positive and negative 1/4. So I'm going to drop to negative 1/4 initially, back through 0, and then we'll rise to positive 1/4. Again, a lot of this, right, as we graph it, we can kind of make our scale however we need to. That said, I'll sort of try to make a point of making this a little bit flatter, right? Maybe that's 1/2, so here's 1/4. Cycle 2 pi, pi. I'm gonna, just to save time, not quite label every single one of these points. We have 1, 2, 3, 4, 5, right? These are our key points. A couple more to grow on. We'll do this guy in purple. So we're going middle, then we're doing a minimum, right? Because it's a negative in front, only down to 1/4, negative 1/4, back to the middle, up to positive 1/4, and then back to 0. So if I draw a line through it, again, I'm getting this same kind of curve, but maybe certainly if I had it graphed relative to one that was going all the way down to 1 and up to positive 1, you know, if I had that as a comparison, you could see very easily how much it's condensed. Something like Desmos is a nice tool to graph a couple of these curves quickly, just like right side by side. So this is y equals negative 1/4 sine of x.